Hi guys, welcome back to the worst YouTube channel on earth. Today is our final review day, as you can see, and the last thing we do before we all get terrible grades. So, let's get started. Whoopee! Alright, so first we learned about geometric mean of two numbers, a and b, so that a over x equals x over b, then x is a geometric mean of a and b, and you'll notice that x equals square root of a times b. Now, we applied this to right triangles, so if you draw an altitude from the right angle of a right triangle to the opposite side, then it forms these three similar right triangles that I'm shading in right now. So if we separate these into parts, we get this sort of medium size, small size, and then the full right triangle. And these are all similar, which can be proven. So if they're all similar, then the measures of the corresponding sides will be proportional. So if you draw on the altitude, then you get one segment of the hypotenuse A, the altitude B, and the other segment of the hypotenuse C. You'll notice that A is actually the shorter leg of one of the right triangles, and C is the longer leg of the other right triangle. So A over B is equal to B over C, because of similar right triangles. So the altitude is the geometric mean of these two segments of the hypotenuse. So if you have the right triangle again with the altitude, then you have one segment of the hypotenuse A, the shorter leg of the whole right triangle B, and the whole hypotenuse of the right triangle C. So A is the shorter leg of the small right triangle, B is the hypotenuse of the small right triangle, but also the shorter leg of the whole right triangle, and C is the hypotenuse of the whole right triangle. Then A over B equals B over C because of similar right triangles again. And these two rules apply to both sides of the altitude, so you could flip around the measurements. Next, we learned about the Pythagorean Theorem, which you know defines the sides of a right triangle. A squared plus b squared equals c squared if it's a right triangle. But if a squared plus b squared is greater than c squared, then it's an acute triangle. And if a squared plus b squared is less than c squared, then it's an obtuse triangle. And a Pythagorean triple are three positive integers that satisfy the Pythagorean Theorem, such as 3, 4, 5, 5, 12, 13, etc. Furthermore, multiples of the Pythagorean triples are also Pythagorean triples, so you can multiply the triples by any number. Next, we learned about special right triangles, so these include 45, 45, 90 right triangles and 30, 60, 90 right triangles. They're special because their sides are in set ratios, so 45, 45, 90 right triangles have sides in a ratio of x, x, and x squared of 2. So the legs are equal, and if the leg is x, then the hypotenuse is x squared of 2. For 30, 60, 90 triangles, if the shorter leg is x, then the hypotenuse is 2x, and the longer leg is x squared root of 3. And you'll see special right triangles in a lot of problems where you're expected to know the ratio, so don't forget these. These are pretty important. Next, we learned about trigonometric ratios, which only apply to right triangles. So a trigonometric ratio is a relationship between one of the acute angles of a right triangle with some of the sides of the right triangle. So let's say we picked angle A right here. The opposite side is the side that's opposite the angle, and the adjacent side is the side that's next to it but is not the hypotenuse. And the hypotenuse is, of course, the longest side. But if we picked angle B, then the opposite side would be angle A's adjacent, and its adjacent would be angle A's opposite. So the terms adjacent and opposite change depending on which angle you look at. So there are three trigonometric ratios that we learned about: sine, cosine, and tangent. And these are labeled sine, cos, and tan. So the sine of an angle in a right triangle is equal to the opposite side over the hypotenuse. The cosine of an angle is equal to the adjacent side over the hypotenuse, and the tangent of an angle is equal to the opposite over adjacent. So remember, the sine, cosine, and tangent of an angle is just the ratio of certain sides that angle will have in a right triangle. And a memory device that you can use to remember this is SOHCAHTOA. So sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So you can use the trigonometric ratios if you know the angle in one of the sides and you want to find the other side. Then after that, we learned about the inverse trigonometric ratios. The ones that we learned about were inverse sine, inverse cosine, and inverse tangent of x. Now, when you plug numbers into an inverse sine or inverse cosine or inverse tangent in your calculator, it'll come back with an angle measure because you use inverse ratios to find angle measures. So if you don't know the angle but you have the sine, cosine, or tangent, then you plug those in. So x is equal to the sine, cosine, or tangent. When you type in inverse sine of x, what you're asking for is the angle whose sine is x. So if you know the side measures but not the angle, you can put the side measures into the form of opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent in order to get the sine, cosine, or tangent, and then plug those numbers into their inverse functions in order to get the angle measure. Alright, let's do an example with a 30, 60, 90 triangle. Pretend that you don't know the special ratios, and the length of the shorter leg is 1. Let's say you want to find the hypotenuse. Now remember, you use the trigonometric ratios when you have one angle on one side and you want to find the other side. So the sine of 30 is equal to the opposite over hypotenuse. the opposite of the angle 30 is 1. So sine 30 equals 1 over hypotenuse. If you multiply each side by hypotenuse and then divide each side by sine of 30, then you get hypotenuse equals 1 over sine 30. Now sine 30 has an actual value, and if you divide 1 by sine 30, then you'll get a number, which is 2. So the hypotenuse is 2. And that's how you can use trigonometric ratios to find side lengths. But now let's say that we didn't have the angle measure, but all we had was the shorted leg is 1 and the hypotenuse is 2. And we want to find the measure of that missing angle. So when we don't know the angle, we use the inverse trigonometric ratios. So we're going to use inverse sine, which means that we have to plug in the actual sine. And we know that the opposite over hypotenuse of that missing angle would be 1 over 2. So if we plug in inverse sine of 1/2, we get that the answer is 30, and that's true. The missing angle would be 30. So once again, the inverse sine, cosine, or tangent of x just means the angle whose sine, cosine, or tangent is x. Alright, next we learned about the angles of elevation and angles of depression. Angles of elevation are basically just formed by a horizontal line and a line of sight up, while the angles of depression are formed by a horizontal line and a line of sight down. So angles of elevation are up, angles of depression are down. And we'll use usually right triangles and trigonometric ratios to solve this. So a typical problem would be you have a person whose eye level is x feet off the ground, and he sees that he's y distance away from an object, and his line of sight to the top of the object forms some sort of angle, and then he needs to find the height of the object. So then you would just use trigonometric ratios in order to find the height of the object and add it to his height. So next we learned about oblique triangles. So if a right triangle has one right angle, then an oblique triangle has no right angles. So an oblique triangle can be an acute or obtuse triangle. Now if you want to solve, that is, find all the angle measures and sides of a right triangle, you can use trigonometric ratios. So if you know the length of one side and one angle, then you can find the measure of the other angle by subtracting 180 minus the angle that you know, minus 90, and you could use trigonometric ratios in order to find the other two sides. If you know two sides but no angles, except the right angle, then you can just use the Pythagorean Theorem to find the length of the third side, and then use inverse trigonometric ratios in order to find the measures of the other two angles. But in oblique triangles, you can't do that because trigonometric ratios only apply to right triangles. So in oblique triangles, you're going to be using the law of sines and the law of cosines instead. So the law of sines says that the sine of an angle over its opposite side equals the sine of another angle over its opposite side equals the sine of another angle over its opposite side. So if you have a triangle with angles A, B, and C, and opposite sides A, B, and C, then the ratio of the sine of one angle over its opposite side is equal to the ratio of all the other sines of the angles over their opposite sides. You can use the law of sines if you're given two angles and an included side. So let's say you have this triangle right here with angles A, B, and included side C. So you can find the angle measure of the third angle by subtracting the other two from 180. Then, after you have all three angles, you can use that to form the ratios. So sine of C over side C equals sine of A over X, which is what you need to find, and sine of B over X. Since you already know the ratios, you can just cross multiply. You can also use law of sines if you're given two angles and a non-included side. So let's say we have this triangle with angles A, B, and non-included side A. So you would once again find the angle measure of the third angle, and then we would use our ratio. So the sine of A over A, which we already have, is equal to sine B over X, which we need to find, equals sine of C over X, and we just cross multiply. So we can also use the law of sines if we're given two sides and a non-included angle. So let's say that we have this triangle here with sides A, B, and non-included angle A. So we can use sine A over A equals sine X over B. Since we don't know what the measure of the angle opposite side B is yet, we need to cross multiply to find that, equals sine of C, since we could find the angle of that by subtracting the other two from 180 over X. However, there's a problem with only knowing two sides and one angle. If we only have one angle and we have two sides set in this situation, we don't know what measure that second angle would form, and it could form an impossible shape. It might not form a triangle at all. Or we might have that there could be possibly two different measures for the second angle, like here, where you can have side B in two different places depending on the measure of the second angle. So for this, we call SSA the ambiguous case. Alright, next is law of cosines. Law of cosines is a bit more complicated. There's one for each of the sides of a triangle. So a squared equals b squared plus c squared minus 2bc cosine of a, b squared equals a squared plus c squared minus 2ac cosine of b, and c squared equals a squared plus b squared minus 2ab cosine of c. So capital A, B, C are the angles, and a, b, c lowercase are the opposite sides. So you can use the law of cosines when you're given all three sides of a triangle. So let's say that you are given all three sides of a triangle. So we have all three sides, lowercase a, b, c, and we need to find the three angles. So let's find one angle to find first. We'll pick the angle opposite the side A. So in order to find that, since we have all the sides, we can just plug in a squared, b squared, and c squared, since we already know those numbers, minus 2bc times cosine of a. So a is the angle that we don't know yet. So with the exception of cosine of a, since we don't know a, everything else is going to equal a number. And so we'll just call that number x. So after you add up a squared minus b squared minus c squared and divide that by negative 2bc, you're going to get x equals cosine of a. And since you know the cosine but not the angle, you can plug your cosine into the inverse cosine in order to find what the angle is. Let's pick another angle. Let's say the angle opposite side b. So we can just repeat the whole process with b squared equals a squared plus c squared minus 2ac times cosine of b, and we'll get what angle b is. After we get what angle b is, then we can just subtract that from 180 along with angle a to get the last angle. So now we've solved the triangle. You can also use the law of cosines if you're given two sides and an included angle. So here we have sides a, b, and included angle c. So first you would find the opposite side c. So you don't know what c is, so c squared equals a squared plus b squared minus 2ab times cosine of angle c. Everything on the right side of the equation you already know, so that's going to equal some number. So you can just immediately find what the length of the third side is. And then after that, you know all three of the sides, and you can repeat what we did above for SSS in order to get one of the other angles. So let's say we wanted to find the measure of angle A, so we would just do a squared equals b squared plus c squared minus 2bc times cosine of angle A. We don't know what the cosine of angle A is, but we know what everything else is, so we can get that to equal some number, and then we'll find the measure of angle A by using inverse cosine. And after that, we can subtract from 180 in order to get the measure of angle B, and then we'll have solved the triangle again. Finally, on to vectors. So, first of all, a scalar is just something that has magnitude, like numbers, they just increase in size. But vectors have magnitude and a direction. So in math, a vector would look something like this. It may look like a ray, but that arrow is actually the endpoint. We can call it the terminal point or the head, while we call the beginning point the tail. We annotate vectors with component form, where we have these brackets and a, b. A represents the x distance from the tail of the vector to the head, while b represents the y distance from the tail to the head. If the tail is at the origin, which is called standard position, then AB is equal to the coordinates of the head. So if the tail of the vector isn't at the origin, and you just have the tail point x1, y1 and the head point x2, y2, so it's head minus tail. So as you can see, when you subtract, you're just finding the x distance between the head and the tail, and the y distance between the head and the tail, A and B respectively. And this would be the same as if it was in standard position, then A would just be the x distance and B would be the y distance. And since it's a right triangle, when you find the magnitude, which is the size or the length, you're just finding the hypotenuse of the right triangle with legs A and B. And if you want to find the direction of a vector is just the angle it forms, usually relative to the positive x-axis. So if you have sides A and B of a right triangle, then you can use tangent in order to find the measure of the angle. So if you have angle theta, then sides B and A, then you can find the angle of theta by doing inverse tan B over A, and that's how you find the direction of a vector, inverse tan B over A. And the vector direction can be anywhere from 0 up to and not including 360. Now when the vector is in the first or second quadrant, everything is fine. The angle can be anywhere from 0 to 180. But as it moves into the third and fourth quadrant, things get problematic. Because tangent values repeat every 180 degrees, then you're going to end up with a direction of the vector that's much smaller than it should be relative to the x-axis. So if the vector is in the third quadrant, then you have to add 180 degrees to the direction that you get from your calculator. In quadrant 4, your calculator is going to give you a negative answer because you're on the other side of the positive x-axis, but you've actually gone almost a full circle around the x-axis. So you have to add 360 to your final degree measure. So if it's in quadrant 3, you add 180, and if it's in quadrant 4, then you add 360. You can also add vectors together. So if you want to add two vectors together, then you just add their x coordinates and their y coordinates. Subtracting is the same. You just subtract their x coordinates and y coordinates. You can also multiply a number, a scalar, by a vector. You just distribute the number to each of the coordinates in the vector. So adding vectors or subtracting them changes their direction and their magnitude, while multiplying them by a scalar only changes their magnitude. Alright, so if you want to add or subtract vectors manually, then you just have to translate the vector that you're adding so that its tail is touching the head of the first vector. Then you just draw a vector from the tail of the first one to the head of the second, and that's your resultant vector. If you want to subtract, then you just reverse the direction of the vector that you're subtracting. So let's say we're subtracting the second one. We reverse its direction, so now it's facing up instead of down, and then we can either translate the tail of the reversed vector to the head of the first vector, or we can translate the first vector's head to the second one's tail. So here I take the latter option, and then I just draw in the resultant vector again from the tail of the first to the head of the second, and I get the resultant vector.